Forces can generally be classified as either conservative or non-conservative. A force is deemed a conservative force if the work done by the force is independent of the path of the particle and depends only on its initial and final positions. Otherwise, it is deemed a non-conservative force. For instance, the work done by a weight depends only on the initial and final positions of the particle and not necessarily on the path that the particle takes. So therefore, weight is a conservative force. In contrast, the work done by a frictional force depends on the total length of the path traveled by the particle as it slides across a rough surface. So therefore, frictional force is a non-conservative force. Two main types of conservative forces we encounter include weight, the gravitational force, and spring force. One type of non-conservative force we often encounter is frictional force. Also note that pushing or pulling forces, including a normal force and tensile force in a cable, are generally not considered to be conservative forces. Previously, we learned that kinetic energy is a scalar quantity that measures the energy of the particle as it relates to its motion. In contrast, potential energy is a scalar quantity that measures the energy of the particle as it relates to its location or position. Potential energy is defined as the amount of work a conservative force must do to move a particle from a given position to a reference datum. We'll now define gravitational potential energy as it relates to a particle's weight. If a particle is located a distance y above a reference datum, such as this particle here above this reference datum, the particle's weight has positive gravitational potential energy, since the weight force which acts downward has the capacity to do positive work when the particle is moved back down to the datum. Contrarily, if the particle is located below the datum, such as right here, gravitational potential energy is negative, since the weight force does negative work as the particle is moved back to the datum. Therefore, if y is defined as positive upward, then gravitational potential energy is defined mathematically as follows, where we have V sub g equals W times y. Next, we will define elastic potential energy as it relates to a particle connected to an elastic spring. When an elastic spring is elongated or compressed a distance s from its neutral unstretched position, the force of the spring does work and thereby stores elastic potential energy in the spring. Whereas gravitational potential energy can be either positive or negative, as we just discussed, elastic potential energy is always positive. So consider the scenario at right in which the spring is stretched positive s from its neutral position. So it's subjecting a pulling force onto the particle, that pulling force on the particle acting to the left. Since the spring force and displacement in moving the particle back to the spring's neutral position are in the same direction, that is to the left, the work done and therefore potential energy is positive in this case. In the scenario in which the spring is compressed, it exerts a pushing force on the particle. So on the particle, we have the spring force acting to the right, pushing on it to the right. To move the particle back to the datum, here, the spring force again does positive work, since the spring force and displacement in moving the particle back to the spring's neutral position are in the same direction, that is to the right. So the work done and therefore potential energy is positive. Therefore, elastic potential energy is defined mathematically as follows, where V sub E equals positive 1/2 ks squared. That positive sign there is really just to emphasize that V sub E is always positive. So whether we have the particle connected to the spring and the spring is stretched, or we have the particle connected to the spring is compressed, the spring always has the capacity to do positive work on the particle to get it back to the datum.